this episode, I'm talking to astronomer Chris Impey about the search for habitable worlds beyond our solar system and how close we are to discovering life on another planet.
So my name is Chris Impey. I'm a professor of astronomy at the University of Arizona in Tucson. And I've worked here. I'm a Brit, but I've worked here for 35 years, long time, because we have clear skies. We have 300 clear nights a year. You can't beat that, certainly not in the UK. And so I work on observational cosmology. My research is distant galaxies and the black holes that they harbor. But I also do a lot of work on education research. And I like exoplanets. So I wrote a book about them because they're very cool. And we know of thousands of them now, which we didn't used to. And they're habitable worlds. And it's a very exciting subject.
Yeah, great. I mean, thanks for joining us on the podcast, Chris. It's great to have you here. As you say, the reason we're talking today really is because of your latest book, which is Worlds Without End, but sort of about all these exciting things that are going on in exoplanet. You know, the search for exoplanet science, the search for a second Earth, perhaps, or habitable conditions, habitable worlds, and perhaps even life beyond Earth. I was sort of thinking the book and the subject matter of the book, Worlds Without End, are very timely because it sort of feels like to me as a sort of outsider to the whole thing that exoplanet science just seems to be just the fastest developing field in astronomy or cosmology. Would you agree with that? And is that indeed why you decided to write the book?
Sure, it is. I mean, before 1995, we didn't know of any planets orbiting other stars, and now we have 5,300, I think, is the current census. So it's very rapid progress. If you plot it on a graph, it's almost exponential. It's almost like Moore's law or sort of information technology, which we're not used to science moving that fast. Perhaps in genetics it does too. So it's very rapid. And of course, it's moving towards something very interesting, which is beyond just gathering more and more exoplanets. You know, after you found the first few thousand, it's like, okay, do we really need 1,000 more? What we're trying to home in on is this issue of habitability and Earth clones, and then the very big prize is the detection of life beyond Earth. Now, we haven't got there yet, but we can sort of see it up ahead.
Yeah, it sort of feels like in the 90s, once those first few were found, that's how it sort of it then just exploded after that. Do you sort of look back and think how, like, it's sort of difficult to remember what it was like before exoplanets, and how did we not discover them sooner, considering how easily we seem to detect them and study them now?
I mean, it's a good question because I do remember. I mean, I've been doing this long enough to remember as a younger researcher, people were looking hard. I mean, the history of the subject is interesting because people had speculated about the existence of exoplanets, since Greek and Roman times, people had wondered. And then through the centuries, as astronomy techniques got better, people tried looking. And the truth was that before 1995, this was a tough field. There were reputations left in tatters, and there were a graveyard of astronomers who claimed an exoplanet and it went away. It wasn't in their data. So everyone was very skittish through the 80s and 90s because there had been many false claims, and it was a tough field. And so the floodgates opened with the first detection by a pair of Swiss astronomers in 1995. But it was still a very difficult thing to do. And so this is a field actually that's been driven by technology. And that's the reason it succeeded in the mid-90s and why the progress has been so rapid. It's basically very precise spectrographs sitting behind larger and larger telescopes that it can tease out these very subtle signatures of a planet around another star.
Yes, that was something I was going to ask you to give us an overview of it, if possible. What methods are there available to astronomers to, first of all, detect exoplanets, and second of all, find out more about them?
So the thing that would be most obvious or seem most obvious is actually the hardest. Let's just take a picture. Just look at a star and look for a planet near a star. And the reason that doesn't work mostly is the reason why this is a hard field. So the Earth, just take the Earth and the Sun as an example. The Earth reflects about 1/1000th of the Sun's light because we don't emit any light of our own. So when you're looking for an Earth-like planet around a Sun-like star, you're looking for something a billion times fainter than the star, and when it's seen at a great distance, it's very close to the star. So it's like looking for a firefly in a football stadium floodlight, right there. And it's just very hard. So that method doesn't work. I mean, we've done it now eventually with great difficulty. So the two methods that were used for almost all the exoplanets that we know of, all 5,000 of them, are the Doppler method, which is looking at the tug of the planet will exert a tug on the star. They pull with equal force. Newton said that. And so we look for the star wobbling because of the planet that's unseen orbiting it. And that was how the first detection was made. And then the other method, if the planet happens to orbit in the equatorial plane, is that the planet could cross the face of the star every orbit. And then the star will dim very slightly as the planet blocks some of the starlight, and then it'll happen again an orbit later. That's a very small signal. For an Earth, it's a 100th% of the sun's light, because the Earth is 100 times smaller than the sun. So that's very hard, and that really didn't succeed until the Kepler spacecraft was launched 2 decades ago. So those are the workhorse methods of finding exoplanets, and they're both indirect. They both don't look at the planet directly. They look at either the planet tugging on the star, and you measure the starlight, or the planet crosses the face of the star, and you see the brightness of the star dip briefly.
So how can we then use that to determine whether or not a planet is Earth-like, or do we apply different techniques to actually find out whether or not a planet is indeed like Earth?
So each of those methods do give you a first hint of what the nature of the planet is, but they don't give you a lot of detail. So the tugging, the gravity tugging, or the Doppler method, that gives you the mass of the planet. So you can say it's Earth mass or close to Earth mass. And you get the orbit, of course, and you know the star, so you know how far away it is, and therefore you know the temperature on that planet. And so now you have a clue to habitability, because you're looking for a planet that orbits a star at the right distance where water could be liquid on the surface. And then the transit method, the one where the star is eclipsed briefly by the planet, that gives you the ratio of the cross-sectional area of the planet to the star. So it gives you the size. So the Doppler method gives you the mass of the planet, and the transit method, or eclipse method, gives you the size. And that's all. And the orbit, of course. And that's not a lot of information. So we've got very, very basic information for almost all these 5,000 exoplanets, and perhaps a hint of habitability, but that's all. It's just very broad brushstroke at this level.
Do we generally find a decent amount of planets that we think were probably habitable, or are they sort of all scorching hot Jupiters where nothing could survive?
I mean, a lot of them are uninhabitable, we think. Also, we have to sort of just take a pause and say that when astronomers talk about habitability, it's a pretty simplistic definition. We're just saying, oh, it's at the right distance from a star to have liquid on the surface. But we don't always know what the atmosphere of that planet is, and the atmosphere makes a big difference. I mean, the Earth is warmed up quite significantly relative to what the temperature would be if there were no atmosphere, by the presence of oxygen, ozone, and of course carbon dioxide, or greenhouse gas. So when you don't know the atmosphere, you can't even really say what the surface temperature would be. And then why does liquid water, why is that so critical? We have life on the Earth that's in deep ocean trenches where there's no starlight, right? So you don't need starlight to have life. The Earth is a counterexample. And we know life on Earth, in extremophiles as they're called, where life can exist above the boiling point of water and below the freezing point. So, we're just using a very simple definition because you have to start somewhere. But you don't, it doesn't really tell you about habitability beyond the sort of these simple ways of defining it.
So does there currently exist any technique or any method by which we could actually detect organic life on an exoplanet if it existed?
We're getting towards that, but I also realized I didn't quite answer your previous question, which is there are habitable planets, and there are definitely uninhabitable planets, super hot Jupiters, like the very first planet discovered. So to put a number on it, it seems like roughly 1 in 3 stars has a planet that might be habitable. Sometimes it's Earth-like, and actually sometimes it's bigger than the Earth. There are a lot of super-Earths out there. In fact, there are more super-Earths than any other kind of planet, and our solar system doesn't have one. So these are things we just learned about by doing these studies. So yes, there are a lot of habitable planets out there. But to go beyond saying it could be habitable and finding if it actually is inhabited by microbes, basically microbial life, that's a very difficult experiment because you have to isolate that planet, that billion times fainter little blip of light next to a star, and take its reflected light and smear it out into a spectrum and look for the signature of things in the atmosphere, gases in the atmosphere that allude to life, like oxygen and ozone in the Earth's case.
Yeah, I mean, it's interesting you're talking about microbial life, because that is essentially what we're sort of talking about here, isn't it? When we sort of talk about life beyond Earth, I mean, you see it even in what we're doing with the sort of the icy moons around Jupiter and Saturn in the solar system. You know, we're sort of looking for places where the very smallest forms of life could exist. Because well, presumably you and we're not sort of talking about technologically civilized species with whom we could actually communicate, are we?
Not really. I mean, again, you're doing the easiest thing first. If life exists elsewhere in the universe, it probably has to go through progression as we did on Earth. So for 90%, people forget, for 90% of the history of life on Earth, you would have needed a microscope to see it. And it was in the oceans. It didn't really crawl onto the land, plants and animals, in the last half billion years. So if we think that's typical, then most planets with life are going to have microbial life, and it may or may not become advanced and intelligent like we are, and it may take a long time, so it might be quite rare. So most of these experiments are looking for microbial life because we think that's going to be more abundant. And also, when microbial life takes grip on a planet, it can change the entire atmosphere, like the 1 part in 5 oxygen we breathe was put there by microbes. So it's a good tracer. It's a good thing for astronomers to look for. But you're right, we would love to know about more advanced forms of life. Now, interestingly, that same method of looking at the atmosphere, that could tell you about technological civilization, because the gases like ozone and oxygen or methane, those are called biomarkers. They're just signs of life, microbial life. But you can also look for something called a technosignature, which is a gas in an atmosphere of an Earth-like planet that indicates technology or civilization. So a good example would be nitrous oxide on the Earth, because that's an industrial pollutant. It just doesn't occur naturally in any abundance at all. So there's some gases which, if you see them in an atmosphere, it's sort of telling you there's an industrial civilization there. But that's interesting too, because of course, once the civilization progresses, presumably they stop being so dirty and messing up their atmosphere with nitrous oxide, and then you wouldn't find it anymore. So it's a little window, perhaps, on a stage of development of a civilization. So all of these are tricky indicators because they're not eternal. They represent a time window of a particular thing that you're looking for.
That's the thing. That's one of the things that sort of occurred to me when I was sort of reading up about this, was the idea that we're not just talking about space, as in we're looking for something that might exist somewhere. We're also talking about time, aren't we? I mean, what are the chances that life does exist somewhere else, that we could actually find it? But also, what are the chances that life exists at this moment, that we could find it, and didn't just exist 2 million years ago, obviously long before we were able to detect it?
Right. So, no, you're right. The real estate of time is as important as the real estate of space. I mean, just to put a number on it, since we were talking about habitable worlds, the research so far, which is mostly in our backyard, the nearest 1,000 or so light years of the galaxy, that projects to, say, 10 billion habitable worlds in the Milky Way. So that's a pretty big number. And that's why astronomers think, well, some of them have got to have microbes on them. They don't have to, but it's likely. Now, the real estate of time is interesting because there were enough heavy elements, and there was enough water and carbon and so on to make an Earth clone that got it in a 14 billion year old universe. The Earth is only 4.5 billion years old. So you could have an Earth out there that had a 7 or 8 billion year head start on us. And life started way back then. And what would that look like? We can't even imagine that. So the real estate of time is very interesting because it means the cosmic experimentation of biology is an experiment that's been going on an awful long time.
Yeah, and it's not sort of all these questions are sort of the concern of this field, astrobiology, which I suppose must be sort of really in its infancy when you compare it to something like astronomy. Um, what what does astrobiology sort of tell us, and is it indeed as young a field as you might sort of expect it to be?
It is a young field. That's, modern astronomy, you could say, started with Galileo, so it's 400 years. And astrobiology, maybe it starts in the 1950s. Miller and Urey did these famous chemistry experiments where they tried to show how life on Earth started by putting ingredients in a flask and adding energy and seeing if you got, anything interesting happening. Well, you didn't get RNA or DNA, but you did get amino acids, and you got organic sludge that could have led to life. So that's a reminder that astrobiology is not just about looking for exoplanets and life on them. It's also about looking at the Earth and trying to understand how life started on the Earth, which we still don't know exactly, and arguing from our own example, the only example we have, what the likelihood of life beyond Earth is. It also means looking at the range of life on Earth, as we were talking about earlier. There's life forms on Earth that don't need a star, so why should life elsewhere always need a star? Well, we don't know how to look for life out there that doesn't have a star, so that's just something we can't do. But life on Earth is telling us interesting things that will frame the search for life beyond Earth.
Yeah, and I think also when you consider like life on Earth and the chances that life would ever have, you know, developed on Earth, but not just sort of microbial life. You know, when you think about like, you know, a dolphin and a cockroach and a human being and an eagle and a tomato and a banana and just all the different things, it's just, I think I always find whenever you sort of start actually thinking about what we know about the rest of the universe and what exoplanets have told us and some of the just completely, you know, hell-ridden, inhospitable worlds. I mean, life, it sort of really brings home just how precious and amazing life on Earth is, doesn't it?
Yeah, and all that list of things you said, you could go from an amoeba to a blue whale. It's all one biological experiment. That's kind of amazing. It is all examples of one thing, really, genetically. And so how different might it be with another starting point on another world, perhaps with slightly different chemistry or different physical conditions. So we should not expect life elsewhere to be just like terrestrial life. That's sort of naive and very anthropocentric. And I think that uncertainty gets larger as you go to the more complex forms of life. I mean, microbes elsewhere may well be like microbes here. Viruses, bacteria, amoeba, whatever, single-celled organisms may just be fairly common. But by the time you get to higher levels of organization, like plants and animals, and then intelligence and so on, I think all bets are off. I mean, it could progress in any number of ways, and it might be very unrecognizable. I mean, my favorite example of aliens, when we're talking about aliens, is octopus, because octopus branched out from our branch of the tree of life almost 500 million years ago, and it's got brains in all its arms and then a central brain, and it has the skin which has 400 million, incredible sacs filled with dyes that can change color and texture 10 times a second. That's insane. And we can't talk to that animal. And if we saw it on another world, we go, oh, wow, an alien life form, amazing. It's intelligent too, because it has complex behavior, as the octopus does. So it's another example of how you try and look at your own planet to learn as much as you can about the diversity of what might be out there.
Absolutely. Um, Also, in terms of just the wider solar system, just you're sort of mentioning, you know, our solar system doesn't have a super Earth. Our solar system doesn't have a hot Jupiter. So, do we sort of learn quite a lot about our own cosmic backyard by looking at other planets around other stars, or other star systems?
Well, we learned something interesting, which is that we think there's a number of habitable spots in the solar system. We think Europa, a moon of Jupiter, it's a water world, could have life under that ice pack. We think even tiny little Enceladus, a Saturn moon, which has geysers and icy jets going into space, it has water under its surface. Titan, which has totally different chemistry based on ethane and methane, that's a moon of Saturn. So those are very interesting places where there could be microbes, and we can't detect those around other stars. There are no exomoons, so the moons around exoplanets, that's just too hard to do. We'll probably get there. in a few years. But at the moment, we don't know how to detect exomoons. And so there are all these habitable locations in our own solar system that we can not detect counterparts of those in other star systems. So it's really, that's another way of saying astrobiology is still a pretty young subject.
Mm. Yeah, actually, there was another thing I was going to get your opinion on, and it's probably quite a tricky question to answer for a scientist. But I often think back to that time before before the first confirmed detection of an exoplanet, and presumably astronomers in the 60s and 70s, and right up to the point that they were actually detected, essentially said it's incredibly likely that they do exist. I mean, how could we only be the only planets orbiting all of, a star of all the stars in the universe? Do you are you tempted to sort of apply that logic to life beyond Earth and sort of say, if we're being honest with ourselves, it pretty much definitely has to exist, or would you not like to go that far?
I think this subject is a sort of test of how rigorously scientifically you think, because the truth is you cannot extrapolate from a sample of one. It's not correct. It's any philosopher or logician would say, no, don't do that. That's dangerous. And so you can get snake bit very easily by doing that. So, you can say 10 billion habitable worlds. They got all the ingredients for life. They got carbon, they got water, they got energy, local energy. Well, how bizarrely fluke-like would life on Earth be if we were the only one out of 10 billion habitable worlds in the Milky Way? Yeah, true, but it's possible because we don't know. I mean, maybe there were flukes involved in the formation of life on Earth. So yeah, as a statistical statement, you'd say, well, very probably there's life beyond Earth, and maybe there's a lot of microbial life beyond Earth. But you put that huge asterisk by it and that caveat because you just can't be overconfident. You can't say too much based on your own example. You're just not allowed to do that scientifically. It's a mistake.
And in terms of the search for a second Earth, if indeed one does exist, do you sort of look at that also in the sense of within the context of climate change and what's happening to our planet? Is there an argument that we're looking for a second Earth because we might eventually have to go there?
I think it's a little more indirect than that. I mean, I think the bottom line is that if there is an Earth clone, and there could be, maybe it's 20, 30, 100 light years away, well, that's still thousands or tens of thousands of trillions of miles. We're not going to go there. I mean, we're probably not even going to send nanobots there. So it's not a realist. There's no planet B. There's no plan B, right? We got to make our stand on the Earth. So it's not helping in that regard. Just like terraforming Mars is not going to help us. Yes, we could make Mars livable, and it would cost hundreds of trillions of dollars and take centuries. And really, we're going to do that rather than take care of the Earth. So what is it useful for? I think the life stories of Earth-like planets elsewhere that we're starting to learn about, they're illustrative. They're interesting because they tell us how stable or unstable our global climate is and our whole planet is, because it depends on geology and other things, not just the atmosphere and not just on us. So there's some sort of lessons in there about what we learn about habitable planets, but they're a little indirect. I mean, if we take our eye off the ball of this planet, then we're really messed up. So exoplanets aren't going to save us.
Um, how do you feel about the sort of, well, as we're recording, it's sort of like the first year really of the James Webb Space Telescope, and it's already teaching us quite a lot about exoplanets, and as well as all the other amazing stuff it's doing. Have you been excited by well presumably you're excited about Webb in terms of your own field, but in terms of the context of exoplanets,
Yeah,
have you been excited about what you've seen so far?
it's a beautiful telescope working extremely well. It's interesting though, for exoplanets, it's going to contribute, and it has done some interesting things. It's not going to answer these problems. It may not even detect life beyond Earth, because remember, it was conceived of before exoplanets were discovered. So it's not optimized for the experiment we're talking about, where you look at the atmosphere of an Earth-like exoplanet for signs of life. It isn't actually great at that job. It's going to do it with great difficulty and take hundreds and hundreds of hours to just observe 5 or 6 targets. It's rather inefficient. So there are 3 huge telescopes all being constructed on the Earth that are going to do that experiment really well with much more light gathering power. And that's what I think will make the breakthrough, the detection of life beyond Earth. One of them is we have skin in the game where it's a 22.5-meter telescope being built in Chile, and we make the mirrors here in Arizona. There's a Caltech and University of California telescope to be built on Mauna Kea at 30 meters. It's a little bit stalled because the native Hawaiians are not sure they want another big telescope on Mauna Kea. And then the Europeans actually are in the lead with their extremely large telescope, 39 meters, also going to Chile. And any of those three telescopes are probably going to succeed, in a field where James Webb will really struggle a little bit to compete.
And that's even though they're ground based and have to compete with Earth's atmosphere.
Yeah, that's a good question, and that's something most people have not been aware of. In astronomy, in the last few decades, we've perfected this technique called adaptive optics, and it's basically your big mirror still doesn't do much; it just tries to be as rigid as possible. But you can make your secondary mirror, the second mirror you use to reflect light back into an instrument, you can make it flexible, very thin, and you can move or flex that mirror dozens or hundreds of times a second. And with that technique, you can take out the atmospheric blurring, so the seeing, as astronomers call it, the jumbling up of an image and the smearing of an image caused by our atmosphere. We've got technology now that can pretty much take that out. And so there are telescopes, we have one in Chile that took a few years ago, took a picture that was sharper than the Hubble Space Telescope. So we've been competing with space head to head on image quality for a few years now. And so yes, these large new telescopes will all have adaptive optics, and they'll all be taking super sharp images, and they're bigger. They have more light gathering power than James Webb, and that's sort of why they will outcompete James Webb on this particular project.
Is that like AI? Is that like a computer fixing it for you, or how does it work?
It's not quite AI. I mean, I think probably neural nets could actually help do those corrections. But basically, it's just you actually use a laser. So you use a laser to bounce laser light off the layer of the atmosphere that's all jumbled up with turbulence. It's just turbulent motions of the gas in the atmosphere. And you register that reflected laser light and use that reflected light to correct in real time the shape of your mirror. So you're sort of gathering information on what the atmosphere is doing to jumble up your image in real time, and dozens or 100 times a second, you're correcting minutely the shape of your mirror to exactly compensate for it. So it's a sort of a closed loop system. It's not quite AI or neural nets, because you could do it before they even were really mature. But it's a pretty clever engineering technology, and it's mature. I remember suffering through engineering on the telescopes we use when all these people doing AOs were always taking our telescope time to play with their toys, and I was just annoyed because stars were out and I wasn't able to take data. But it was worth it, because after all the engineering and all the time they took to get it right, it does really work now.
Awesome. Just finally, I mean, are you going to, now that the book's written and it's out, are you going to leave exoplanets for now? Like, will you come back to that field, or do you sort of have have projects and questions to ask elsewhere?
I mean, I'm still attached to it as a subject because it's so exciting. I think there's going to be a little interim here before we detect life, the first microbial life, and then things will get really hot again. I'll probably re-engage, but I think maybe for a while I'll go back into cosmology, look at some, start caring about distant galaxies and supermassive black holes and things like that. They've been sitting there, wanting some more attention, so I think I'll go back to those for a while.
Does the are you sort of more excited about what Webb can do in that respect?
Absolutely. So Webb's killer app, and the thing it was really built for primarily, was first light, to detect the very first galaxies, and also by extension the first big black holes in the universe. And there's every sign that it'll do that experiment really well. So yeah, that's going to be very exciting. When did the first stars form? When did the first galaxies form? Actually, which came first, like chicken and the egg? Was it the first stars or the first galaxies? And what about the black holes? How did they start? Because we know in the nearby universe, galaxies grew over 14 billion years, and we have big beefy galaxies with billion solar mass black holes. Well, how did that all happen? Where did it start and when?
Doesn't it feel like we're on the precipice, both in terms of that and also in terms of exoplanets and search for habitability? It feels like within the next 20 years, some absolutely incredible revelations could come about, doesn't it?
Absolutely. I mean, in cosmology, we have some huge problems, issues, or enigmas like dark energy and dark matter. We really haven't got too far with those. So that's, you could view that as the glass half full or the glass half empty. I mean, that's a challenge, and it's exciting to have the two biggest ingredients of the universe that you don't know what they are. It's an opportunity, I guess.
Fantastic. Cool. Well, thanks for coming on the podcast, Chris, and good luck with the book when it comes out, Worlds Without End.
Yeah, it was fun to talk.
Yeah, maybe we'll hopefully get you in the podcast again some point, maybe to talk about dark matter or the sort of the dawn of the universe.
That would be fun. It's good to talk to you, Ian.